Remember, if you have T and R, and there's a non-trivial connection here, this gamma TR, so that tells you that the geometry here is not going to be discernible just by drawing a perpendicular axis on a flat blackboard or something like that, because there's a warping. So this is actually, let's say, straight, right? And this is actually curved. What you need in the geometry are something that helps you correct for that curvature. And that's exactly what these things do. If you measure the connection curvature of the space, those connection curvature pieces tell you exactly how to compensate. Now, in a more sophisticated theory, you're going to have several connection components for a space, not only one. The whole thing together will be called the connection, an affine connection. Now, we have to be careful because we're looking at this in two different perspectives. Here, we're drawing this as perpendicular axes and on a flat blackboard, and we draw this as curved, and we're saying really in a curved, if a diagram which reflected the curvature of the space-time, it would be a straight line, but we don't have such a diagram. Okay? One could, concoct such a diagram. Or, since space-time is curved, if we drew this in real space-time, it would be, how do you draw it in real space-time? Just let something fall. And you don't see it, you see the trajectory, or you see a series of points, but the world line of this thing is a straight line. So we can draw it in that sense, but it doesn't really help us much because what we're seeing, this straight line that we're seeing is a succession of points, the trajectory. But that's not what we want. We want the world line, and the world line is in fact straight, even though it would be drawn like this.
Right.
So we can, I'm now drawing a straight world line in space-time. I just can't see it. I'm creating a straight world. Now, what we're saying in our theory is that instead of looking at this as a flat kind of plane TR, and this world line is curved, let's measure this curvature, which we measure by R double dot. And then we'll say, now let's create a theory of a curved spacetime. Not a flat spacetime like this, a curved spacetime, where the connection curvature of that space is given by R double dot. So it's a different thing. Okay, this curvature of the line here, R double dot, now will specify for us what will be the connection of that curved spacetime. Okay? So when you look at this thing, it has two different meanings. In a flat space-time diagram, just a naive space-time diagram, draw your 1 over r squared diagram, the calculus curvature, and then you get R double dot, which is the acceleration. Okay, that's just, calculus. Nothing here unusual. But what we're saying is, okay, now do differential geometry and create a curved spacetime, where that curved spacetime, since it has curvature, has connection curvature and has Riemann curvature, where the connection curvature will be this. Now, that's not really accurate because once you have a real curved spacetime, you can have maybe several curvatures, you can have something else, and the curvature is not necessarily going to be exactly this. What we want, though, is a theory where curved spacetime, give it a connection curvature, which will look to us from the flat spacetime perspective as a world line curvature of R double dot. That's really what we're saying. Okay, we have no right to expect that the actual connection will be R double dot. The connection has to be something that when you use the correct dictionary to translate it into the flat kind of perspective, it'll turn into a world line with this calculus curvature of R double dot. If we're lucky, it may turn out to be exactly R double dot. It could be, but we can't expect it. We should certainly expect that when we measure the connection curvature for the space-time, let's say right here on the planet Earth, right outside the Earth, since this theory of R double dot works so well, right? I mean, you can measure things and it works with R double dot, right? We would certainly expect that the new theory should give us the same values here. So whatever it is that arises in the new theory as the connection for that space-time should either be R double dot or something very, very similar to R double dot, so similar that you wouldn't even measure the difference right here. You might measure the difference somewhere else where our theory breaks down. Very, very important thing to keep in mind. You can't represent the geometry of a curved surface by using a flat surface. It's going to err in various ways.
Right.
And if we're going to draw space-time on a flat blackboard like this and say this is space and this is time, all right, and we're going to draw a world line, well, very nice. We got a curved line for a free-fall world line. That's simply because we're drawing curved space-time quantities on a flat surface. All right, our gamma TR that we defined was simply the calculus curvature of this curved line. If we have a full four-dimensional curved space-time theory, in that space-time, this would actually be the straightest possible line. It will be a geodesic, right? And it'll have some connection curvature. Now, we expect that since this theory works, the Newtonian theory works, and this acceleration gives us the right answer, that when we find the full theory's geodesic curvature, the connection curvature, it should be very, very similar to this curvature that we found, which is the acceleration. 4 cases where Newtonian theory works well. Okay, but you always have this kind of mapping of different theories in which you can see, but you cannot expect to find the geometry of a curved spacetime by using a flat board. Okay? If we find out that our theory tells us that there's curvature here, maybe we could draw this on the surface of a globe. Imagine the globe, and we draw a t-axis and an r-axis. So let's say the r-axis is the equator, and the t-axis is a line going up from the equator to the North Pole. Right? And then we plotted the acceleration. And the acceleration would be this line on this globe, and then we would find it's actually a great circle. So it's actually geodesic. That would be if the curvature of space-time were exactly the curvature of a sphere, which in fact it very much is for the interior. Remember, we found the interior tunnel solution has constant tidal forces, tidal acceleration.
Oh, yeah, right.